Hi, and in this MicroVid, we'll be continuing on with the topic of breathing mechanics. Specifically today, we'll be talking about forced expiratory flow, or FEF. Now, before we define FEF, or forced expiratory flow, we need to talk about a different term, and that is forced vital capacity. Forced vital capacity is the amount of air expired from total lung capacity to residual volume using the most forceful expiration maneuver possible. Or another way to say this, it's a maximal inhale and then forcefully pushing out as much air as possible. And forced vital capacity can be abbreviated FVC. Basically, as the name implies, it's the vital capacity, the total amount of exchangeable air, forcibly exhaled. This also can be done from a maximal exhale and then forcibly, maximally inhaling all the way to total lung capacity. So now that we know what forced vital capacity is, forced expiratory flow is the volume change over time during the middle half of FVC. So what do I mean by that? So let's take a look at what FEF, or forced expiratory flow, looks like. So in your notes, figure 25 is a spirometer recording of volume on the y-axis versus time, and we're looking at a FVC, or a forced vital capacity. So you have the person right here breathing normally, right there, breathing normally, and then they do a maximal inhale, and then what happens is they do a maximal with as much force as possible exhale to residual volume. And that's what this is right here. This to this is residual volume. So what we can do with this is divide the time that is spent exhaling into seconds. We can divide it into forced expiratory volume 1 or forced expiratory volume 3. And right here would be right in the middle, if you want to draw a line right there, that would be, you guessed it, FEV2. So we can divide this up, and what's important to note is the slope right here. This red line looks at FEF, the forced expiratory flow, between we said the middle half, because that's what FEF is, it's the middle half of an FVC. So it's really important to keep all of these acronyms correct in your head so that you do not confuse them. We've got forced expiratory flow, forced vital capacity, and forced expiratory volume. And usually FEV is split up into FEV1, 2, and normally it doesn't take more than 3 seconds to fully ventilate, forcibly ventilate your vital capacity. So why is this important? Well, based on the slope of this red line right here, so we've got our red line right here, I'll draw over it in red again. Based on the slope of this red line, it will tell you how functional your lungs are. And this slope will change in varying disease states. So let's look at how the slope changes in different disease states. So here is figure 26 in your notes, and this is an example of different disease states. We're going to use our normal versus emphysema versus pulmonary fibrosis, and we see that the FEF, which is the measure of the slope of the forced vital capacity, and it's the middle portion of that, it's the slope right here. And so we see the slope is really the same in, or very similar in both the normal versus the fibrosis. However, if we look at the emphysema, the slope is drastically different. And you can see that here. So these disease states will change a forced expiratory flow. Now this makes sense because remember that during emphysema, you have decreased lung recoil. So it's really hard, because you have decreased lung recoil, it's really difficult to exhale. So a forced expiratory, or a forced vital capacity, which is the maneuver where you blow out as much, you breathe in maximally and you blow out as much air as possible. This is going to take a little bit longer because you don't have that added recoil to aid in emptying the lungs. Now with pulmonary fibrosis, you actually have more lung recoil. So the slope is very, very similar to what a normal one would look like. Now on this graph, this shows what this forced expiratory volume, or this forced vital capacity, what this looks like in the three disease states. So we were looking at an FEF, a forced expiratory flow here, what it looks like in those three states. Now we're going to take those same three states, that is normal, someone with emphysema, and someone with pulmonary fibrosis, and we're going to put them on individual graphs and look at a forced expiratory flow, what that looks like over time. So in a normal person, we look at their FEV1. That's the amount of air that can be forcibly exhaled in 1 second. So FEV1 is the first second of that. And you can see that this is the volume of air that can be blown out in 1 second. Let's look at someone with emphysema. It is drastically different. We see that someone with emphysema, because they have decreased lung recoil, the volume that they're able to expire is significantly lower during the first second. And if we continue to look on, the total amount of volume that they're able to expire is significantly lower than even a normal person. So let's go to fibrosis now. So when we look at fibrosis, we see someone with an FEV1 that is still lower. Look at this. The FEV1 is still lower than an FEV in a normal person. So an FEV1 in a normal person, or forced expiratory volume 1 in a normal person, is larger than both the FEV1 of someone with emphysema, someone who has decreased lung recoil, and also a normal person is larger than someone with pulmonary fibrosis, that FEV1. Now, what's interesting to note here as well, I'm going to erase this so we're not too confused. What's interesting to note here as well is that we can take the ratio, the FEV1 over total FVC, over total vital capacity, and this gives us a percentage. And so when we look at someone with an FEV1 of a normal person, we see that they can get about, it looks about 80 to 90%, let's say 80% of their total lung volume out. So they're really only lacking this much that they can't get out in that first second. Someone who has emphysema, though, in the first second, they can really only get about, because they don't have increased lung recoil, they can only get about 60%. So there's a larger gap right here in terms of percentage. Okay, there's a larger percentage here with someone with emphysema. Now, someone with pulmonary fibrosis, on the other hand, if you look at their FEV1, they can expire almost all of their forced vital capacity within the first second because they have increased lung recoil. So they don't really have much left after that first second. So when we look at the FEV1 over the FVC in terms of a percentage, someone with pulmonary fibrosis has a greater FEV1 over FVC than a normal person, and a normal person has even greater than someone with emphysema. All this to say is that these measurements help respiratory physiologists understand how these different diseases work and affect different functions related to the respiratory system. So to sum up, we've looked at forced expiratory flow, we've looked at forced vital capacity, and we've also looked at forced expiratory volume 1, 2, and 3, and how these three change during several disease states such as emphysema, fibrosis, and how they also are in a normal person. I hope that this has been helpful.